Chapter 4 is linear transformations. So the definition, a linear transformation is a function. So it has inputs, outputs. It's we'll call most of them capital T for transformation, and it'll be from V to W, where inputs will be in one vector space V, and outputs will be vectors from another space W. To make it a linear transformation, instead of just any function, it has to obey these rules, that if you add two vectors together, then it doesn't matter whether you add them in the input or output. So you can add them first, then apply the transformation, and you should get the same thing as if you apply the transformation separately and add the results. Call that preserving addition. And the same is true for multiplication by a scalar. It doesn't matter whether you multiply by the scalar first and then apply the transformation, or apply the transformation and then multiply by the scalar. And that's preserving scalar multiplication. And together it's preserving linear combinations. So here's an example of a transformation from R2 to R3. So the inputs will be two-dimensional and the outputs will be three-dimensional. And we have to say what it does. So we do that with variables. So the transformation on any vector xy is equal to x plus y as the first component, 2x, and negative y. So there's three output components using the two input components, and so you get a vector in R3. So here's an example. If you take t of 3, 2, then you'll get 3 plus 2 is 5. 2 times 3 is 6, and negative 2. So let's check and see that that's a linear transformation. What we'll want to do is see that it always preserves linear combinations, as in doesn't matter whether you do the transformation before or after the combination. So we can do that all at once. We'll take c times xy plus zw and see that we can pull out the c and separate the addition. So if you do the linear combination first, multiply by the c and get cx and cy, add on the z and the w, then you're applying t to using t on cx plus z and cy plus w. So you add them together to get the first component, multiply the top one by 2 to get 2 times cx plus z, and just take the negative of the second component, so negative cy plus w. But then you can quickly rearrange those three components one at a time, and you can put the cx and the cy together next to each other in the first component, and then pull out a c. And if you do that in the second component, the only part that has a c is that first half when you multiply it by 2, so we'll have c times 2x. Probably the quickest way to do it is to look at the result I have here and see that it does give you what you have in the previous line. If you multiply by cx plus y and then add on z plus w, you get cx plus cy plus z plus w. If you multiply c times 2x and add on 2z, you could pull out the 2 and get 2 times cx plus z. And if you have negative cy and negative w, that's also the same. But then looking at this way of writing it, you can tell that that is exactly the same thing as applying the t to just x and y, and the t to z and w, and multiplying the first one by c. So we've seen using variables that it doesn't matter whether you do the linear combination before or after for this transformation. Therefore, it's linear. A quick example of another input is the 0 vector. So for the 0 vector in R2 is 0, 0. And in this case, if I use this same t, I get 0 plus 0, 2 times 0, and negative 0, which is 0, 0, 0, which is the 0 vector in R3. Now, this is always going to be true. For any 0 in the input vector space, anytime 0, when you take 0 in the input vector space, t of that 0 vector is equal to the 0 vector in the output space. It might be it might look different, but it has to be, that has to be true. And that's because it preserves that scalar multiples. And if you just use the scalar 0 as the scalar multiple, you'll see that that is always true, that t of 0 equals 0. If not, it's not a linear transformation, which doesn't mean that you can check for a linear transformation that way. If you can check that it's not a linear, you can see that it's not a linear transformation if it doesn't happen. But if it does, you still have to go back and check the whole rule that it preserves linear combinations.